In this lecture, we'll be discussing the last discrete random variable distribution in Chapter 3, the Poisson distribution. The Poisson distribution is very closely related to binomial distribution. In binomial distribution, we are dealing with Bernoulli trials, and the binomial distribution random variable x was used to quantify the probability of number of success within a fixed number of trials n trials, while in Poisson distribution the random variable was used to quantify the number of hits success within a certain time space area. Therefore, the variable was used to quantify the number of success or number of hits within a continuous process. And this continuous process is occurred over a span of time, space, or area. And if you can imagine, if you can slice the time period into infinite number of small segments, then for each given segment, you can treat that as a Bernoulli trial. Whether or not that specific event occurs within that period of time, the small segment is treated as a Bernoulli trial. Either success means the event occurs, or failure, the event doesn't occur. And the Poisson distribution, later on I will discuss further. You have very small probability of the success within a small segment of time, but overall you will have average rate of occurrence. For instance, once every century. Let's look at a few examples to give you a better idea about what I'm talking about. So a few examples. The first example, let's say the earthquake is a fairly rare event. It can hit LA area at the average rate of 1 per century. Therefore, if you divide the 1 century time into days, let's use days as a day as a unit, then each given day, the probability of earthquake is very small. Therefore, we quantify that using a long period of time. Over 1 century, we probably have one this rare event occurs. Therefore, if you use each day as a Bernoulli trial, then any given day you either have earthquake or not have earthquake. So it satisfies the condition of Bernoulli trials. And oftentimes we are interested in projecting the future. We want to know what's the probability that over the next 10 years the chance of earthquake will hit LA area is how much, and that probability can be calculated or quantified using Poisson distribution. The second example is related to quality issues in manufacturing. Surface defects occur on an instrument panel at average rate of 6.7 per square feet, and this 6.7 is the average rate. So that was obtained by maybe examining 100 square feet area and found out that you get 670 surface defects. Then divided by 100, you get the average rate of 6.7 per square feet. So this average rate doesn't have to be a whole number. The third example is a large nursing home finds average rate of 10 strokes per month among their patients. This can also be approximated or can be quantified using a Poisson distribution. So this kind of events or process, we call it Poisson process, and the probability associated with this kind of process is Poisson distribution. In general, a Poisson process has the following three features. First, the hits or success occur randomly at the long-term average rate of lambda per unit time, unit space, unit area, depending on the situation. And secondly, the likelihood of a hit is independent of time, space, area, i.e. the past 1 hour is as likely as another. Past doesn't affect the probability of future. The third one is it is negligible that the chance of simultaneous hit. Like for instance, in the earthquake, we don't consider the situation where you have 2 earthquakes occurring at the same time. So that's almost impossible, because this one is in a specific area, like LA area. We don't take that into account. So Poisson distribution don't treat those simultaneous hits. Probability mass function for Poisson distribution. So when we have a Poisson process, we usually have those information available. The first one is the lambda, which is the average rate of hits, and the second information is the time period that we are interested, so usually will be stated in the problem statement. The third one is the variable defined as, which is the number hit within the time period that we are interested in. And the probability mass function here is S equals to K. Well, the K can be any number greater or equal to 0. So this very likely over the period of time that you are specified, there could be no event hits occur. So this K goes from 0, 1, 2, and all the way to infinity. And you can plug in the K into this formula to calculate the probability for the number of hits equal to K. Well, here the lambda and the T are given usually in the problem statements, and the K is the parameter. It should also be given in the problem statement, so you just replace those parameters with the number in the problem statement. And here we often use the capital lambda to replace the lambda multiplied by T. So remember, the lowercase lambda is the average rate of hits, multiplied by T is the average rate of hits per T time instead of per unit time. So this is the probability mass function is e to the power of minus lambda multiplied by lambda to the power of k divided by k factorial. So as I mentioned, there's a very close relationship between binomial and Poisson. So where does the Poisson equation comes from? Well, it actually comes from binomial. If we have, for a binomial distribution with n is the number of trials, p is the probability of success for each given independent trial, and let's assume that n is close to infinite, goes to infinity, while the probability of success goes to 0. So it's very small probability, but this extreme infinite large number multiplied by extremely small number, and the product goes to a constant lambda. This lambda is equal to lambda multiplied by t in the Poisson distribution. And if we want to know what's the probability of number of success within that time period, we can use binomial distribution. X follow binomial distribution with parameter n and p. and this the binomial probability mass function for probability x equal to k. And this formula, if you have n goes to infinity, p goes to 0, and n multiplied by p keep as a constant of lambda, then this formula is approximated by this formula. This is the formula for Poisson distribution. So you can treat Poisson distribution as infinite number of Bernoulli trials with small probability, while the product n multiplied by p keep it as a constant. So let's look at one example of Poisson process. For the case of thin copper wire, suppose that the number of flow follows a Poisson distribution with a mean of 2.3 flow per millimeter. Here, this 2.3 is the lowercase lambda. Find the probability of exactly 2 flows. So what these 2 flows is the number of flows we are interested in. This is the k in the formula that we just described, and here we want to know the probability of exactly 2 flows in 1 millimeter wire. So this 1 millimeter is the length of interest. So the 1 millimeter is our t, lowercase t. So let's use x to denote the number of flows in 1 millimeter wire. Then what we have is t equal to 1 millimeter, and the capital lambda is equal to lowercase lambda multiplied by t equals to 2.3 flow per millimeter multiplied by 1 millimeter equals to 2.3 flows per millimeter. And the question asked for is the probability for, sorry, this should be x instead of s, so I probably should replace this with s. Denote s as the number of flows in 1 millimeter of wire. Then we have s equal to 2 equals to e to the negative lambda multiplied by the lambda to the power of k divided by k factorial. We replace the numbers for those parameters. E to the power of negative 2.3 multiplied by 2.3 to the power of 2. 2 is the k. Okay, this one is the k. And divided by 2 factorial, you get the probability equal to 0.265. Okay, so this problem we're dealing with the probability mass function. And for Poisson distribution, we can use Excel to calculate that fairly easily, and the function that used in Excel is just the name of the distribution, Poisson parentheses k is this k, lambda is this lambda, and the last parameter is true or false. And if this one is the last parameter is true, then or true is also equal to 1. True, then this function is calculating probability, cumulative probability distribution function. So it's equal to probability of s less or equal to k, because the probability cumulative distribution function is defined like that. But if you assign a false value to this one, to this function, then what you are calculating is the probability as equal to k. It's the probability mass function. And in our problem, we are actually calculating s equal to k, so we should set this parameter to be false. That's exactly how we get it. So you just type in the Excel cell, each one of the cell, put it in equal Poisson 2, which is the K. Okay, 2.3 is the lambda, and also the last one is the fourth. Then we are basically calculating probability S equal to K. So you will get the same value as we get from this equation. Let's extend the problem a little more challenging. Here we want to determine the probability of 10 floors in 5 mm of wire. So what have been changed? What have been changed is, one is the probability of 10 floors instead of what's the probability here? It's 2 floors. Now we want to know the chance of 10 floors. The other thing is we are not examining 1 mm wire. Instead, we are looking at 5 mm wire. You can imagine if the length is expanded, you should have higher chance of seeing floors. So therefore, let's use X to denote the number of floors in 5 mm of wire. Then here the T is equal to 5 mm, and the capital lambda is equal to lowercase lambda multiplied by T is equal to 2.3 multiplied by 5 equal to 11.5 floor per 5 mm. And the probability that we are interested in, so sorry, this should be S, another typo here. So S equals to 10, which is here, is equal to the e to the power of negative lambda multiplied by the lambda to the power of k divided by k factorial. So you plug in 10, replace with the k, you find the probability here, 0.1129. And similarly, you can use the Excel to calculate that probability. So you can see from this example, hopefully you understand what the lowercase t means, what the k means in the formula. Okay. Another example, the same problem statement, but we ask the third question is determine the probability of at least 1 floor in 2 mm. So these keywords you should already seen multiple times. So at least means greater or equal to 1. To solve this problem, we still denote the number of floor in 2 mm wire instead. So whatever being specified in the problem statement, you should use that length, time, or space. Then we have T equal to 2 mm, and the capital T is equal to 4.6 floors. And we notice that we are interested in calculating the probability X greater or equal to 1. And greater or equal to 1 means X can be equal to 1, equal to 2, equal to 3, equal to 4. It requires infinite number of terms. So how do we deal with that? We can look at the problem from the complement point of view. The complement of X less or greater or equal to 1 is the opposite side of the equation, is probability X less than 1. When we look at X less than 1, there's only one case, which is X equal to 0, because the X has to be non-negative integers. So X greater or equal to 1, this probability is 1 minus the probability X equal to 0, and this one, X equal to 0, is a complement of X greater or equal to 1. And X equal to 0, you can simply plug in to the formula with K equal to 0. So we end up having a very high probability, 0.9899, to have at least 1 floor in 2 mm wire. So in the Excel, you can use the same Poisson function to calculate this probability. So to summarize, if x is a Poisson random variable with parameter capital lambda, which is the lowercase lambda multiplied by t, then we have the expected value of the Poisson random variable is equal to the parameter lambda, and the variance sigma square is also equal to lambda. So the mean and variance of Poisson model are the same. This is very important conclusion. Both mean and variance are the same. For example, if particle counts follow a Poisson distribution with a mean of 25 particles per square centimeter, the variance is also 25, and the standard deviation of counts is 5 per square centimeter. So here, remember, it's the variance and the mean are the same, not the standard deviation and the mean the same. So these two are the same for Poisson distribution. The standard deviation is the square root of the mean. If a variance of data is much greater than the mean, then the Poisson distribution would not be a good model for distribution of that particular random variable. But this usually, when you apply Poisson distribution to certain phenomenon, trying to approximate that particular process using Poisson distribution, you should check whether or not this approximation is valid. And an easy way to check that is look at the equality of variance and the mean. So these two should be fairly close in order to use the Poisson distribution to approximate or to model that process. Okay, that's about Poisson distribution.